Good morning. I'm audible to you guys. Okay. So today we will start with hashing. Okay. In last class, I gave you a brief overview of hashing, means why we need a hashing. So hash table is basically a data structure, and in the hash table, we just store data with the help of a mathematical function. Okay, and that function is called your hashing function or hash function. Wait, let me share my screen first. So this is just your comparison table for all the sorting algorithms we have already discussed. Last class we discussed about this. So just come to the hashing part. So hashing is just a technique for mapping a large set of arbitrary data to tabular indexes using a hash function. So in hashing, basically two components will be there. One is the hash table and other is the hash function. So in the hash table, we are going to store all the data. Okay, and hash function will be a mapping function which will map every item in our hand to certain slots of the hash table. Now the thing is why we need the hash table. Remember in the last class I told you guys, like suppose we need to store a large information about employees with the help of phone numbers. So, if you have a very large data set and you want to search for particular item, because whenever we store the data, there will be three primary functions. One is search, insert, and delete. Correct? So, if we use a if we use an array to store employee data or any data, uh, if you want to search for something, it will take O n time, correct? Searching time complexity for searching any item in an array is log big O of n time for the worst case. Again, suppose we are going to search an item with the help of binary search tree or binary search tree. Now it's binary tree, binary search algorithm. So if we use binary search, then it is going to take log n time. Even if we use binary search tree, then also it will take binary log n time. So if you use a normal sequential approach or linear approach, then it is going to take O n time. And if you are going to take a divide and conquer approach for searching anything, it is going to take log n time. But the thing is we want it to be very fast. Okay, so we want that searching, insertion, deletion, everything should take a constant time. So we want a O1 time, a constant time. So for that, hashing technique came around. So in a hash table, normally we keep data in terms of key and the data. Then each key is mapped to a value in a hash table. And normally those keys are used for indexing those data. So just like any other array or anything, the main operations or basic operations on a hash table will be searching, inserting an item, and deleting an item. Okay, so let's see the direct table concept first. Okay, direct table is also a hashing, but a slightly different. So what is hashing? Suppose we have certain keys. Okay. Hi. কোনো নাই হেৰি আহিছে চাগে মালাবা আহিছে নিজৰ নাই নাই হেলমেট থৈ দিয়া so suppose we have certain keys are like 8 পিছত গৈ আছে 8 3 13 and 6 and 4 and 10 these are the keys we have, and suppose I have a array, or you can say just a hash table. Okay, suppose these are our this is a hash table, or I can say it's just an array. So what is hash function or hashing? We are going to take these keys and use the same key as the index to store that data. Okay, that means what? If the key is 8, I am going to store this 8 value at index 8. Okay, if my data is 3, I am going to keep it in the same index value 3. If it's 13, 13 will go to the same index value 13. For 6, I'll store it in 6. For 4, it will be in 4, and 10, it will be 10. Okay, so this is your direct table access or direct access. Okay, so this is the direct access table. So what happens here? Direct access table is used when the amount of space used by the table is not problem for the program. Here we assume that the keys are small keys and number of keys are not that too large, and two data have the same key. So limitations is that the key should be small and the number of keys must be small enough so that it doesn't cross the size limit of array. Okay, now come to this point here. So as you can see, I'm just storing the values at this index. That means this 3 is your key. See, right? Now again, this is the key 8. Now suppose I want to add, now if you want to search for anything, any item, then you can just say the index key 3. Suppose, so I'll just search in the index 3 and I'll get my key. So it is going to take a constant time, or I can say O1. Now see, the size of the table is 14. Okay, now I want to add one more item. Suppose it's 50. Okay, now if I want to store the 50, then the problem is my table is not that big. Here, the concept I'm using is that, wait, the concept we are using that whatever will be the value, I'm going to keep it in that same index. Now the size of that hash table is just 13 or 14. So if there's any bigger number is there, then space is not enough. Okay, then another problem is that suppose we have taken a sufficiently large hash table, then again there will be lots of empty spaces. Okay, that's the limitation. So we have to make sure that our key values are smaller in number. So if we have smaller number of keys, then only it will be sufficient to put in a hash table. That's the limitation of your direct access table. Okay. Okay. I'm saying something. We have to invest lots of memory. Yes, correct. Memory will be wasted because there will be lots of empty spaces. Again, if you want to add anything, you need to provide a bigger hash table. So this is your simple hashing, or you can say direct access table. So there is a modification to this method. Okay. What is the modification is this table? This is your main hashing. So just keep it there. So in direct access table, we just keep the keys, and the same index, we just keep the value. Okay. So second approach is your main hash table. Okay. Or your hashing function. So what happens in hash table here? We use a mathematical function. Okay. In direct access, we just use the same value at index. Here we are going to store the value by mapping those keys with the help of a mathematical function. That mathematical function can be anything actually, and whatever will be the result of that mathematical function, that will be the index for that particular hash table. So let's see here. So these are the keys, okay? So I can just draw it like 8, 3, 8. These are the same numbers, 13, 6, 4, 10, and just skip 10. Okay. So these are the keys we have, and these keys are known as your key space. Okay. These are your key space. Now you have a hash table. Just consider it as a like inverted array. It's fine even if you take like vertical array, it's fine. 5, 6, 7, 8, 10, 11, 12, 13, and just think it as a 14. Okay, 14. So now what happens here? This is the key space, and this is our hash table. Okay, this is our hash table. So what we do here, we just use a mathematical function which is known as your h of x. For example, this x is your key space. So this function will take a x value. Okay. This is just representation of this same thing. Okay. In this case, I just simply told you that the value will be the index in itself. So just that the same concept, I am just converting it into a function, and the function is h of x is equal to x. That means whatever will be the key value, those will be the x again. That means 8 will be stored at 8, 3 will be stored at 3, 13 will be stored at 13, 6 will be stored at 6, because it is 3, 6, 8, 13, 4 just store at 4, and 10 you just store at 10. Okay, so this is your normal function. Then again the same problem, right? If I want to add one more space, our hash table is not enough, correct? Because the size is just this much. So remember, for any function we had two types of cardinality. One was 1 to 1 and other is your many to 1. Okay, so this is your 1 to 1 function. So you can see that if we use one-to-one function, the problem is that our hash table and the key space is not enough. Okay, so for the most of the cases, for hashing means the normal hashing, we take many to one. Okay, many to one, that means we just select a hash function such a way that it will just map multiple values to a single data or anything. Okay, for example, for this case again, I'm going to take a hash function. Since we have problem with one-to-one cardinality, so we are going to select a hash function such that we can just deal with our smaller size of hash table. Okay, suppose our time is 1, 2, 6, 8, and 9. Suppose now my table size is 10. Okay, so here hash table size is 10 and this is your key space. Now I want to use a hash function which will just give me the size of the table. Okay, this is the function which I'm going to use to map the keys into the hash table. So this function will take the key and it will find the modulus of the size. Okay, size of the hash table. Now here, what is the size? It's 10. So I'm saying hx equal to x mod of 10. Okay, so this is the hash function I'm going to use to map all the keys, or I'll use to map all the keys to the hash table and store in the hash table. This is our hash table, correct? So this function, what will be the answer? So for example, 8. 8 modulus of 10. What is the remainder? I'm taking key 8 and 8 modulus of 10 is 8. Okay, so I'm going to store 8 in 8. Okay, now I have 3. Again 3 mod of 10. Remainder is 3 again. So I'm going to store it in 3. Okay, so now you can see, now it's not exactly depending on the value and the index. Instead, it's just taking a smaller space. Correct? In the previous case, it's just one-to-one. So every time we need to add an item, we have to make sure that hash table is really big enough. Now here we are minimizing the size. Our hash function is dependent on the size of the hash table, so that whatever value we have, it just fits there. Okay, again, yeah, there will be a problem. I'll discuss about it a bit later. So just see this one. So this is the simple, so this is the hash function I use. So whatever will be the key, I'll just take the modulus with size and I will store it in the hash table. Now 13. 13 modulus of 10, remainder is 3. Now you see it's 3 again. But in 3, there's already an item there, correct? So this situation is known as collision. Okay, so since it's many to one mapping, that means what? Multiple keys can map to the single value. So in this case, this situation is known as collision. Okay, so in a hash table, there are certain methods to handle these collisions. Okay, for collision handling, we have two methods. One is open hashing and one is close hashing. Okay, the same thing as in slide also. So in the hash table, the limitation is that the same index is produced by the hash function for multiple keys. So conflicts arise and this situation is called a collision. To avoid this, a suitable hash function is chosen, but it is impossible to produce a unique key. Thus, a good hash function may not prevent a collision completely. So we just need to reduce the number of collisions. Okay, we can try to select a good hash function, but the thing is you can never get rid of collision problem. So the main idea or goal will be to reduce the number of collision. So, okay, I'll come to this good hash function later. So what we do for the collision? The collision has two types. One is open addressing and other is close addressing. Close addressing is also known as your chaining. Okay. So this is the part I'm going to see. So chaining, why it is chaining or open addressing? Sorry, close addressing. So in this technique, if a hash function produces the same index for multiple elements, these elements are stored in the same index by using a doubly linked list but it requires a additional memory in the table. Okay, so what I'm going to do here, since 3 and 13 is taking the same space, instead of storing it like this, I'm going to use a linked list. Okay, so I'm not going to directly store it in the table, but I'll just store it in like a linked list. So 8, I'm going to store it in a linked list with the help of a pointer. There will be a pointer here. Then since 3 was previously here, so first I'm going to keep 3 in the linked list. Okay. Next, I map 13. So 13 is in the same index. So I'm going to just put it in another linked list. So whenever I'll see there is a collision, then I'll just keep it in the linked list form. Now it's 6 mod of 10, no problem, you can just map it there. So I'm just going to keep it in a linked list. Next is 4 mod 10 is again 4, so I'm going to keep it in 4. And next is 10 mod 10 is 0, so I'm going to keep it in here. Okay, so this is the chaining process. Okay, so whenever collision occur, if we use chaining method, what happens in chaining? We just store the value in the form of linked list. We do not directly store in the hash table. Instead, we just use the pointer and store it in a linked list. Now, searching is again one thing, but if it's a linked list, then there's again a problem. See, if you are looking for an item 13, you will just use this hash function, right? Then 13 mod 10, then you will get 3. Now first you will go to the pointer 3, then you will move here 3, then again you go there and you will find a 13. So whatever searching approach we use in a linked list, the same thing will be used in this case also. So the extra memory will be required and your time complexity is not constant again, but it's again will be better than your login time. Okay, so this is the chaining approach. Okay, is this clear? This is your open addressing actually. Chaining approach, is it clear? Okay. Now next approach is your close hashing, and one of the very popular one is your linear probing. Okay, linear probing. This is your close hashing, and this open hashing is also known as chaining. So what happens in linear probing? Everyone chaining is clear? Just let me know. We are in case of what? In case of chaining, we are not going to keep things in hash table, but we will keep in a linked list or doubly linked list. Okay. So whenever we get a collision situation, we are just going to keep it in the same index, but the thing is, it will be in a linked list format. Okay. Now let's see what happens in linear probing. Okay. Okay, 0, 1, 2, 3, 4, 5, 6, 7. Okay. So again, my size is 10. I'm just taking the same thing. So what happens in linear? I'm going to use the same thing. Okay, this is your key space. This is your hash table. And our hash function is same thing. It's just x mod of table. Table is your, sorry, size of the table. So it's the same function we are going to use here as well. Okay. So first 8 mod of 10 is 8. I'm going to store it in 8. Okay. Next, in this case, what I'm going to do is that our function will be a little bit different. Okay. Okay. First, let me just show it. Okay. So 3 for 3 mod of 10, it will be stored in 3. Okay. Next, 13. Okay. 13 mod 10, remainder is 3. So now you see 3 is already full. Okay. So in linear probing, what we do, if the space is already full, then we are going to just store it in the next available space. Okay. So since index 3 is already full, then I'll just use the next available index. It is pointing to 3, but the thing is, since it's already full or occupied, I'm going to store in the next available space, which is 4. Okay. Now I have 6. 6 mod 10 is 6. I'm going to keep it in 6. Next, 4. 4 mod 10. 4 mod 10 is what? Tell me 4 mod 10. Yes, correct. It's 4. Now see, the 4 is already occupied, correct? Now what I will do, linear probing, I'll just use the next available space, which will be 5. So I'm going to store 4 in 5. Now 10, again 10 mod 10 is 0. So nothing here, I can just directly keep it here. So this is the linear probing approach. Okay, so linear probing, you can just say it's slightly means modification of this function. So what we are doing here, if I'm using hx this, so I'm using a modified version, and your modified version you can say as like h of x plus f of I, function of I. Okay, I is your index and rest is the same, is the size. Okay, so means I'm telling you just next available space, right? So for this thing you need a hash function, right? You need to modify this hash function. So this is the approach. So your f of I is I here. Okay, so it's just linear approach. So f of I is I, and I can go from 0, 1, 2, 3 and so on. So what happens, our collision occurred in 13, right? The 3 was just place in its exact place. Next, 13 was there. So what happened for 13 here? You can see h of 13, correct, plus f of 0, because I will start from 0, correct, and rest will remain the same. Okay, so h of 13, and this hx is nothing but your main hash function, correct? So value is 3, and f of 0 is the I, means f of 0 equal be 0. So it's just 0 and size, that is your 10. So again 3 more 10 is 3. Okay, so what I'm going to do here, h13, since this one is already occupied, we can see, so I'll try with the next index. Okay, 13, h13 plus, now f equal to 0, I have already used, f equal to 1, and this is the size. Okay, so h of 13 is your old hash function, which is 3, and f of 1 equal to 1, that means 10. So 4 more 10 is 4. So we came to the next index 4. So 4 was empty, so I inserted in 13. So same case in case of 4 also. First I'll start with 0. Then if it is already full, then I'll just keep I1 and so on. So this is the equation for your linear probing. So same thing you will find in here as well. Okay, this is written open. Linear probing, your function is hk of k plus I. I'm just saying that I is your f of I. Okay, this is the basic one. Okay, again, so this linear probing is clear. Linear probing and chaining. Everyone, chaining and linear probing. Ma'am, I is for index. Yes, I is for index. Is it clear to everyone? Chaining and linear probing. Okay, others? They partially said yes. Okay. So there's another function. Okay. The problem in case of linear probing is that you can see all the keys are just clustering around same locations. It has a problem of clustering. Okay. Can you give a summary, just a overall explanation? Yeah, okay. So what happens in chaining? So your hashing is what? Hashing or hash table is a data structure where we store any data in terms of key and the data. So in normal hashing, what we do, we can just keep all the things like whatever will be key will be stored in the uh, same index. If your key is 8, you are going to store it in the index 8, and if 13, you are going to keep it in 13. So whatever will be key, so you will store that value in the same index. So this is called your direct accessing or direct access table. It's also a hashing. Okay, but the main thing of hashing is that we convert it into a mathematical model. So for hashing, you will have a mathematical function, and with that mathematical function, you are going to map all the keys in a key space to the hash table. Okay, hash table is just a table. So for the hashing table, you can have, this is the normal key space one. The problem is there, there is lots of empty spaces, and if you want to add anything, you have to make sure that your hash table is sufficiently large. Okay, so we have to find a hash function such that it can be a many to one function. We don't want this. Okay, if we use this one, this will be a direct accessing thing, so the complexity of searching anything will be O1, but the thing is it will require lots of memory and it will be a wastage of memory. So we want a hash function such a way that it depends on the size. Whatever is the size of our hash table, so we will try to select our hash function in that way. Again, yeah, of course, in this case also, if you want to add some more item, there are certain problems. Your hash table may be not that big enough. If you want to add more items, it's going to need uh, more space. So if your hash table is dynamic, if your hash table is dynamic, so if you require any space in future, it can just dynamically allocate it. Okay, so anyway, so main hashing is that we will find a function which will be in like dependent on the size of the hash table, so that in minimum space we can store our keys. Okay, so this is your basic hash function. X mod of size. Size is the size of hash table. So whatever will be the key, we'll just find the modulus from the size. Okay, then you are going to store it like this. Again, when you are going to map using this function, there will be certain cases when the index value, whatever value it will generate, that can be a same value. So two key space or three key space can have same index values, and that situation is known as your collision. Okay, again, that means what, we cannot find any unique values for index, so only goal is to reduce the number of collision. So to reduce the collision or handle the collision, we have two types of solutions. One is chaining. So what we do in chaining, we use the same thing. It can be many to one, means your data will be not directly stored in the hash table. Instead, it will be stored in a linked list. So if your data will have the same index, it will just use a pointer to a linked list node. Then again, you, if there's another element which will have the same index, then will another pointer to point to another node. So in case of chaining, we are going to store everything in the form of linked list. Okay, and the other method is the linear probing. Okay, so what happens in linear probing? Linear probing, we will just uh, if the indexes are same, then we are just going to use the next available free space. So here you can see 3 is 13 has function will give you the 3 index is already occupied, so I'll just store it in the next available function. So again, in case of 4, it's giving me 4, but the 4 index is already occupied by 13. So I'm going to store it in the next available space. Okay. So for this linear probing, the equation is like this. Okay. So you are just going to use the same hash function, just that there will be a function of I, and I is nothing but your index. So first you will try with the same logic, hence it's just a little bit modified version of your original hash function. So you start from 0 for 13, index is 3, but 3 is already occupied, so I cannot store it there. So I'll just start index from 1. I will start from 0, 1, 2, 3, 4. Okay, so it's not exactly index for this table. Okay, don't get confused. The I is not the index of this table. Just remember, I is just will start from 0, 1, 2, 3, and so on. First you will use the value 0. If it has a space, it will just store it there. If space is not available, it's already occupied, you will try with the next index, which is 1. So for 1, using this function, the answer is 4. So 13 should store in index 4 of the hash table. This is the calculated index of hash table. Okay, this is index of hash table. This is the calculated. Now 4 was empty, so I inserted 14 or 13 here. Okay, so again I do it from the 4, then I'll start with 0 if 0 means it should be 4, and then I'll start with 1 if I use 4. See, for 4 mod of 10, index is 4 and it's just a linear function, right? Start with 0, it will be 0. So for this case it will be 4, and 4 is already occupied, so I'll start with 1. So if I use 1, so it will be 4 plus 1 equal to 5. So 5 space was empty, so I just placed it there. Okay, this is just equation. Just remember, the main concept is whatever available space is there, you are going to store it there. So if suppose some index is there which will point it to 4. Okay, now if suppose I want to add 50, just imagine. Okay, so for 50 it will, okay, just think I want to store 40. Okay, 40 should point to 4, correct? Now 4 is already occupied, it has 13, so I'll come to the next point. Now 5 is already occupied, correct? So it's not available. Again I will come next. Next position is 6, it's again occupied, so I'm not going to store it here. So I'll come again. So I'll store 40 here. So main concept is, if that particular index is not available, you will just keep come linearly and find the next available space. And just that the equation for linear probing is this one. Okay. So this is the overall view. In next class, I'll tell you the other types of hashing. We will discuss the same thing tomorrow also. Okay. And there's two more things. Quadratic hashing. Quadratic hashing is that, okay, it will be too overloaded. I'll explain tomorrow. Okay. So that's all for tomorrow, means today. Tomorrow we will start with the problems with linear probing. Then there will be quadratic probing too. This is linear probing, there is quadratic probing, then there is double hashing. Okay. So we will just use check with them later on. Okay, it's going to end. Stop sharing and take your attendance. Hashing is a very important concept. Okay, hashing concept is used like almost everywhere, starting from the database to cryptography to compilers, everywhere. It's a very important concept. Okay, just remember the concept very well. Okay, same using hashing, there is encryption algorithms and all. So hashing is a very important one. Okay, okay, for today I hope everyone is clear. It's most of the time Dullar is saying yes, yes, and then Deepa says yes. I am not sure about the others. Okay, so I'm going to end the meeting now. Thank you.